Hello. Okay, let's get straight into it. We don't have much time. So, smart contracts testing, very interesting. Medusa versus Foundry. I know a lot of us here will use Foundry, right? Great. So, we're also looking at something called Invariant. We're going to have a very short code walkthrough, and then we're going to jump to the rest of it. So, testing, smart contract testing. I know we have a lot of Web 2 devs here. You know what testing is. Unit testing, what does it do? Unit testing. So it's a kind of test whereby you are testing a chunk of a code base. So let's say you have a very large code base and you just want to know what is happening in a specific function. That's a unit test. Integration. It has to do with I want to know how this like 2, 3, 4 functions in a particular context, how they work together. But the emphasis on this my presentation today is actually on invariant testing. And if you're in the smart contract world, I know you have heard this once or more than once. So what are invariant? Invariant are basically properties. So when you develop a smart contract, there are conditions in which must stay true. And these conditions are what we refer to as invariant. There are things that no matter what happens in your contract, they must not change. It must remain the same. Do we get that? Because we're going to need it later on. It must not change. So those are what that is what I am referring to as invariant. And like I said, a lot of us, we are familiar with Foundry. Foundry is a framework that we are actually used to actually build our smart contract. You can do a lot of things there. You can code, you can force, and a whole lot of things. But today we're looking at Medusa. Medusa is basically a forcing framework. It does just one thing, and what it does is forcing. But you can also force on Foundry. But in addition to that, you can code, you can run your test and do all sorts of things in Foundry. And Medusa also does one thing. Medusa works across board. Medusa works across board. So you can use Medusa with Foundry. You can use Medusa with ADAT and all one. Can you guys hear me very well? Okay, great. I'm trying to rush through so we can meet up with the time. So when it comes to invariant in smart contracts, we have two types of invariant. We have the function level and we have the system level. Like I said, we're going to check this in the code base. So the function level invariant are just like unit tests. They have to do with a particular function. But the difference between a function level invariant and a unit test is that you have the opportunity to actually play around with a large value. So for example, if I want to do a unit test for a function, I have to impute my parameters. So x is 10, b is 20. But when I'm forcing, I don't have to specify what x is. I don't have to specify what y is. The forcer is actually going to pass in a whole range of values. So it keeps trying 0, try with 1, try with 2, try with 3, depending on the type that you're using with it. So which means that I can easily know that, if I'm using an unit 256 as my parameter, it's actually going to start from 0 to the max. Does that make sense? Okay. System level, on the other hand, has to do with the whole system. So when you are building a protocol, when you are building a smart contract, there are stuffs on a level in which must remain the same. And in the code walkthrough we're going to do, we're going to see some of them. For example, if you actually, if you have a max deposit, which we're going to see in the code walkthrough, if you have a max deposit of, let's say, 1 million in the protocol you are developing, and then you say, this is the max deposit that this protocol can take. And then when we start depositing funds, you can actually have a system level invariant that says that the deposit must not actually exceed that max deposit. That's the system level. It means that a lot of things need to happen. People need to deposit. You're not checking at the function level, but you're actually going a step further to check it at the system level. We're going to understand that better. So let's jump into the code straight up. Do I need to increase the font, or you guys can see it very well? Is it clear now? Okay. So this is a very simple smart contract called savings. What can you do in this smart contract? You can deposit you can withdraw, and you can get interest per annum. I think that's clear enough. Hello? Is that clear enough? You can deposit, you can withdraw, and then you can get interest per annum. And then we have a couple of interesting variables. We have a max deposit, like I mentioned before. We have a max deposit amount. We have a minimum deposit, and we have a couple of mappings. We have total deposited and blah, blah, blah. So what are the invariants in this small contract? So this is going to give light into what we have been talking about. So the first invariant is user deposit must increase by amount added after deposit. Does that make sense? User deposit must increase by amount added after. So when a user actually deposits a particular amount into the protocol, when we check the balance of the user inside the savings contract, it must actually increase by that amount. Does that make sense? Number 2, user balance must decrease by amount withdrawn. So when a user decides to, let's say, I want to withdraw a particular amount from my savings, when we check it, it must actually see that the particular amount we withdraw is actually equal to when we actually check the balance, right? Does that make sense? The third one is that deposit must not exceed contract max deposit. The example I made before. So if we go back to the contract, we'll see that we have a constant max deposit, and then we have coded it right there. So we're saying that in this, one of our invariants is that no matter how much, once we get to that amount, we don't want users to deposit this is a system invariant. We also have another one that says users must get interest after every year. So at the end of the year, every user must be able to get interest per annum. And then the last one says that user must be able to withdraw at any time. So this is where we go into Medusa. Like I said, you can force with Foundry. It's quite straightforward. You can do that. But like I also mentioned, Medusa, it's a forcing framework. It does not. That's the only thing it does. So it gives it that very interesting feel, and then you know that all what I'm doing here is forcing. You can go to on Google and search for Medusa. You can add Medusa so you can find it easy, and you can download it and start using on your laptop. So what are the things that we need to do to start using Medusa? So the first thing that we need is to identify the invariant. It's very, very important. So Medusa does not have any strength without your invariant. And like I mentioned before, if you actually want to force, you need to have a LD understanding of the code base you are trying to force. It is not magic. So, okay. So, forcing. So, the short hand is force. So, force, I'm actually still going to show us. So, what we mean by forcing is that we actually, let's say we have a function, right? And then that function has a parameter x and y that we're passing into it. On a normal day, if we're writing a unit test, we're actually going to pass in 10 and maybe 20, and then we'll run it through. But when you are forcing, I don't need to pass anything to it. I just leave it at x and y. So what the forcing engine or the forcing framework does is that it actually generates that x and y value on its own. So it doesn't just do that, it actually does that for a wide range. So for example, it can do that for, let's say, x, if we're using in Solidity, if you're using something like maybe unit 256, it can do that from 0 to the max of unit 256. So your unit test is actually specific for a particular scenario. But when you are forcing, you're actually forcing through the spectrum of all possible values. Does that make sense? So but invariant testing takes it to another level. Because when you are forcing, like I said, there's a function level forcing, which is the one I just explained now. But system level is that, okay, a lot of things happen in the system. We are actually depositing, we are withdrawing, we are getting interest. What are the properties of the system that must always remain true? So we can also go as far as actually checking those levels and making sure that it's always true. And like I mentioned, we have two invariants here that are actually very, very important, which is the system level invariant. We have the ones that say that deposits must not exceed contract max deposits. You can say you can't really test this with just a function, because a function means one person is actually the one, you're just doing one action. It's something that you may need about maybe 1,000 transaction plus before you can actually get to a point of testing this. So it's not really physically possible for you to do, like, to test this. So that is where Medusa comes in. So as I was explaining, we have a couple of things to do. I'm assuming that we are going to get Medusa and we're going to install it. So I don't want to go through all those. So identify the invariant. That's the most important thing. That's the most important thing. You have to identify the invariant. It's very, very important. It's when you have your invariant that you can now start using the fuzzing framework that you have. So the next thing you need to do is one of the first functions that you run when you actually want to start is Medusa init. We're all familiar with init. So what Medusa init does is that it creates this JSON. So this is basically a where you actually put in your properties, that things that you like the settings for the old fuzzing suite. And there are a couple of interesting things here. I'll just touch in some of them. One of the very important thing here is the target contract. So this is me just saying this is the contract that I want you to actually use for the fuzzing. I'm still going to show us this, so just note that target contract, very important. And that thing that's also very important is the corpus directory. This is where you go in to check your coverage. So Medusa also gives you a kind of way to check that, because it is possible that you are fuzzing, but you are fuzzing wrongly. Just the same way that you can test. You can do right unit test and you are testing rubbish. So you can actually fuzz and you have a feeling that, oh, I'm fuzzing something, I'm doing something, I'm a fuzzer, but you're not doing the right thing. So that is where the coverage comes in. So you can be able to see, you can see what is actually going on there. So another interesting thing that Medusa does is that it gives you the ability to actually include more than one users. So when you are fuzzing in, let's say, Foundry or some other frameworks, you can only, by default, you can only fuzz with one user at a time. So you need to actually write a lot of boilerplate to actually fuzz. But Medusa actually comes, I can even add more. Currently, by default, it comes with 3. You can say sender address. You can add like as much as you want. So by default, when I run this, my fuzz on Medusa, it's actually 3 users actually doing all those deposits, withdrawal, and all 3 users by default. But I can add more. And so on and so forth. We can check the rest. Let's go straight into our fuzz test. So this is the folder invariant, and I'll just go straight to savings. There are a lot of things I will not mention, but I want to just go to the core of it. So the first, like we're saying here, it's just like a smart contract. Like it's just like a normal contract that I'm writing. But this is actually my fuzzing contract. So the first thing I did was I imported the savings that we saw, the tokens I'm using inside the savings. Medusa has a cheat sheet that you can use for things like pranking that we are familiar with in Foundry, and they added something called total balances for my test. So the first one, user deposit must increase by amount added after deposit, which I mentioned, right? That's my first invariant, and this is a test for it. What did I do? The first thing I did was mint some tokens to the user, ms.sender, prank the user, approve the amount for savings. I'm tracking the total balances, and the first thing I did was to get my pre-balance. So the reason I'm getting my pre-balance is so that I can have a point of comparison. So I get my pre-balance, save the money, get my balance after deposit, and then I do my assertion, which is after balance minus pre-balance equals to amount. Does that make any sense? I'm just trying to check that I have deposited this money now, and I get my balance. So when I subtract my balance after and my balance before, I should be able to get the amount actually deposited, right? So, and then I'm testing with the assertion, and if it goes through, that means, if it remains true, that means the test passes. So that is the first invariant. The second invariant is the withdrawal. So we are going to notice something here that I'm not doing anything. I'm not trying to like do the deposits or anything. I just go straight into withdrawal. You're going to feel like what's going on. So which money are you actually trying to withdraw when you have not deposited? So Medusa does something interesting, that it calls all those functions, like all these functions that we have in this file here, it calls them randomly. So it calls deposits, calls withdrawal, calls. So what is happening here is that when I call this test deposit here and I'm passing ms.sender, remember I mentioned that we have multiple users. So it calls all those users randomly, calls deposit. So the user already has some amount. Calls another one, he has some amount. Then calls another random user and calls withdraw. Does that make any sense? So it's doing in such a way that it's not straightforward. It's a magic. It's not straightforward. So in that way, we're actually mimicking real life a scenario. Is that fine? Is that clear? Okay, so let's go to the next one. So withdrawal is basically just withdraw some amount, and then like we did for the first one, we get our pre-balance, we get our after balance, and then we check the assertion to make sure that we're actually withdrawing that particular amount. Okay, so this third level, which is the system level, deposit must exceed contract mass deposit. This one is very, very straightforward. All I need to do is know the total deposited in the contract and make sure that is always less than or equal to the max deposit. Does that make any sense? So if we go back to our savings, we'll discover that there is a variable there, total deposited, which is actually tracking the total amount of tokens that all the users in the contract are depositing, right? And in my test here, by invariant test, I'm trying to say that, okay, in this contract, I want to make sure that the total deposited is always less than or equal to the max deposit, in which I have said that this is the max number that I want people to deposit. Does that make any sense? So this is a system level invariant. System level invariant. Okay. Okay. So in the test withdrawal, we're doing the pre-balance. So I know you guys, I'll talk about these total balances later on. So then I'm doing the withdrawal, pranking the image of sender, then doing the withdrawal, then getting the after balance. That's all. The deposit is coming from. So like I said, Medusa does this stuff that it calls all those functions randomly. It calls deposits, calls withdraw, calls everything that is in this contract. So that means that user probably already has a deposit. When it calls, that image sender you are seeing actually is like 3 users randomly being called. So it already has, if it doesn't have, it's going to fail on the back end. It's not going to tell me, it's going to fail until the user actually has an amount before he can call the withdrawal. So it's actually working very fine. So you don't need to you would have done that if you are doing a unit test. What you're saying would have made sense. But now we're actually forcing. We are not restricted. So what Medusa does, it just calls them randomly. And at the point, each of those users will actually have some deposits and then they can withdraw. Does that make sense? Okay. So I think the mass deposit is very straightforward. And then we also have the get interest, which we're actually warping the time. So those that are familiar with Foundry, they know what warp. So we're basically just increasing the time. And you will discover that in all these things that we are doing, we are not specifying amount manually. You can see, like I mentioned before, the amount is just there. Hello? The amount is just there. We're not doing any 10 ether, 1 ether. So every time that it calls deposit, it actually just puts in any amount randomly. So let me run. I think my time is running. So we have get interest. It does the same thing with time. And like I mentioned, you need 1 year to be able to get a particular interest. But in Medusa, because we can actually warp the time and we can get time randomly, we just run random time and we can run through it. And then the last one, we have that tests have enough to pay deposit, which means that at every point in time in this protocol, the contract must be able to pay deposit. And how are we checking that? We're checking that by making sure that the total balance inside the savings is always greater than or equal to total balances, which was this. You guys notice I've been tracking these total balances, and I did that in. Okay, no, I'll round up now. Okay. So I did that in the test deposit, and I did that in the withdraw. So to track when the user is actually depositing and when the user is actually withdrawing, and that gave me the opportunity to be able to actually test this. So let me just run Let me run the test so we can just see one or two. So the command is Medusa force. And when I run the command, what was that? I'm in the direction. The pressure.
Yes, pressure. The pressure is real.
Okay, coming. Okay, something is not right. Okay, okay. I think I know why. I deleted something that is erroring out. Okay, that's fine. Without this, we have not done a demo yet. So, wow. What's really happening?
I'm sure we can. I'm sure.
Don't worry. Okay, so it's running.
It's running. Sorry. I'm always the devil's advocate.
So we can see it cuts the first one, and we can actually trace the path. You can see in test max deposit. It means that at the point in time, the invariant for test max deposit actually fails. Why is that? And we can also look through the sequence that is being called. We can see it called test deposit, and it calls test mass deposit. Are you guys still with me? So if we actually go through the function, we are going to notice that the get interest is actually going to be a problem because we're not actually putting any extra funds into the protocol. So by the time the part it calls the get interest, we're actually going to take part of the funds that's supposed to be for the normal user, but the actual issue that you actually caught here is the issue of max deposit, which means at the point user actually deposited more than they should, because when we look at our savings dots, so we'll discover that in the deposit we're actually not checking to make sure that the users have actually gotten to the max deposit. So this is one. The other one is one I just explained now. So I guess I have to stop here. I hope you guys enjoy my talk. Thank you so much.
Thank you very much.